All right, so we are taking a look at 3.5 here today. Chances are that we skipped 3.5 when we were doing 3.1 and 3.2 and the other sections in Chapter 3 because related rates is something that I tend to sometimes leave until a little bit later. So some of you are taking a look at this section after you've already been in Chapter 7. So this is related rates in your textbook, the Red Stewart Calculus. It's section 3.5. Now, what are related rates? Well, in a related rates problem, we are given the rate of change of one quantity. So we're given a rate of change, and we're asked to find a rate of change of a related quantity. So we're talking about two separate rates of change here. So if we've got a couple variables, and each of them are changing, okay, these problems are dealing with the rates of change of more than one variable at a time. So it's a little bit, there's more things changing. To do this, okay, to figure out a related rates problem, we find an equation that relates the two quantities. So that's pretty straightforward. We've done this before when we talked about maximizing and minimizing. Okay, an equation that relates quantities. And then we use the chain rule to differentiate both sides of the equation. This is the one thing that's different here, with respect to time. Okay? So a related rates question, we will be dealing with two changing quantities and the rates of change for two separate quantities. And we're going to differentiate with respect to time. Now that's different than differentiating with respect to one of the variables, right? So as time passes, we are examining the rates of change of both of them, both quantities. Now it is going to be easiest to explain this with some examples. So I'm going to quickly move to some examples here after you've had a chance to copy that down. Alright, so let's examine example 1 here. This is a related rates question. See if you can pick out the two rates of change that we're dealing with here in the question. A spherical snowball, okay, so we're talking about a snowball, and they're telling you that it's in a perfectly spherical shape, so that we can use a certain formula, right? It is melting in such a way that its volume, the volume of the snowball, is decreasing at a certain rate. And that rate is given as a decrease of 1 cubic centimeter per minute. So here is rate number 1. Right? Here is a rate that is given. The question says, at what rate is the radius decreasing? So we've got volume decreasing, and we're asked for what is the radius decreasing at? What rate is the radius decreasing when the radius equals 5 centimeters? So if we take apart this question, rate 1 will be given here as the volume decrease. The other rate that we're dealing with, rate 2, is the radius decrease. So volume decrease, radius decrease. Now, this part right here is the moment, okay? It's not a time unit, but when the radius is exactly 5 centimeters, the question says, that's when I want to know at what rate it's decreasing. So when the radius is 5 centimeters. So this is sort of the stipulation or the constraint, okay? So this is the, we want to find out how I'm going to put this. Find rate 2 when r equals 5 centimeters, okay? So we've got rate 1, rate 2. When there's two different rates involved, it's a related rates equation. Now, how do we want to go about solving this? Well, it says here in the notes that you took here, we find an equation that relates the two quantities. So how are volume and radius of a sphere related? Can you think of a formula or an equation that relates the two? How about the volume of a sphere formula? Okay, so you shouldn't have to reinvent the wheel here. Lots of times there will be a given formula that you've worked with many times in the past. So what's the formula for volume of a sphere? Anybody remember? The volume of a sphere? It would be 4/3 times pi times the radius cubed. So this is the equation that ties together the volume and the radius. All right. Now, okay, this is where it gets a bit different from the other questions as well. We've got two rates. So which is the preferred variable? Well, that's the kind of the language, that's the thought process that we've been using so far, right? Which one is the preferred variable? Are we going to do dv dr? Right? Are we going to do dr dv or something different? And in this case, we're doing something different. In a related rates question, we differentiate both sides of the equation with respect to time. So what that means is we have two quantities, volume and radius. Those are the two quantities that are changing, right? The volume is decreasing. The radius is also decreasing at the same time. And so we differentiate with respect to time. So we find dv with respect to time, and we also find dr with respect to time, which means that, don't get too confused by this, all it means that is that the derivative dv over dt is v prime. So v is not our preferred variable. The derivative of v is not 1. The derivative of v is v prime. You see, it's not with respect to volume. Okay. Also, dr dt, what that means is that the derivative of r with respect to time is just r prime. That's all that means. So you don't get too excited about this, like, oh my goodness, such a difficult question. It's not really. We're differentiating both with respect to time, which means that neither of these variables are the preferred variable. Okay, once again, the derivative of v is not 1. The derivative of r is not 1. Okay? Now, if you look back here too, related rates, right? The rate of change. Do you remember what that language, when we used that language before, what does that mean? It means what's the rate of change of a variable? It's the rise over run, something else? What are we talking about over here? Slope, which is also what's the word I'm looking for? The derivative. The rate of change of a variable is the derivative of the variable, right? The derivative is the rate of change. So that's why we differentiate both sides with respect to time. Okay? Okay, so let's just, let me just erase this here to make some space. Hello, there we go. Okay, erase. Clean this up a little bit. Okay. So, v prime, is this given in the question anywhere? Look at this question again. Is v prime, the instantaneous rate of change of volume, is that given in the question? It is, right here. Look at, the volume is decreasing at a rate of, there we go. The derivative of the volume is, now it's decreasing at this rate. So that's minus 1, or negative 1. So v prime is negative 1. You don't have to include your units in the problem here. I'm not too sticky about that. But you are going to have to make sure you go back and find out what your answers mean, and what the units are. All right. What's the other rate of change? The radius is decreasing. So guess what? That is r prime. Is that given? No, actually, it's not given. We are trying to find the rate. You see, at what rate? Question mark. So this we do not know. But what we do know is we want to find that these rates of change only apply at the radius being 5. So when the radius is 5. The most common mistake that students do is this. They plug r in here, they find v, and they're done. You cannot do that. Okay? This is not what this question is asking. You may not do that. And why is that? Well, I'm not interested in what the volume is when the radius is 5. I'm not. I'm interested in what is the rate of change of the radius as the volume is decreasing by this amount at the point where the radius has decreased to a point where it's exactly 5. So at that point in time, what is the rate? So do not plug this variable into the equation at the beginning. Okay, you cannot do that. Make a little note there. Okay, don't plug value in at the beginning. Okay, what you have to do is differentiate first. Differentiate. Okay, first. So we're not going to plug that in. We're going to differentiate. Okay. All right, clean it up a little bit there again. All right, good. So what is the derivative of v with respect to time? It's v prime, right. Good guess. What is the derivative of this side with respect to time? So that means we have to include an r prime in there. So what is the derivative of that side? Do we have to do the chain rule? Well, consider this. This is a number, and this is a number. Okay, pi is an irrational number, but it's still just a value. It's a constant number. So really, we only have one variable here, and what we're going to do is the power rule here. So this is going to be 3 times 4/3 pi times r squared. Now, in a sense that, did you guys ask about the chain rule? Right? So in a sense, okay, yeah. With the r here, right, when we take the derivative, we don't deal with r right away. So we do have to multiply by r prime. So yes, it's a chain rule, but I thought somebody said something about product rule. So I just wanted to tell you that this is not a product, but power rule and chain rule. So yes, those. If you asked about chain rule, yes, we do chain rule. And if there was more involved on this side, we would do chain rule over here too, for sure. But we just differentiate with respect to time, which means that there is no preferred variable at all. Okay, so this is the derivative with respect to time. So now what we do is we fill in all the values that were given. So v prime is -1. So guess what? Put a -1 there. All right. Now this here, we can simplify this. This is just 4 pi. Right? What is the radius at this point? Here it's 5, so now you put in 5. Okay? And then r prime. And we're trying to solve for r prime, right? So now you have everything filled in except for r prime. And now we can solve, right? So this is 100 pi, so -1 over 100 pi equals r prime. And we want to simplify that. That is, the radius is decreasing at about, this is about 0.03. And so you would say, therefore, I haven't shown you this too much, but those 3 little dots there, that means therefore. Lots of times in science, you're doing a report or something, conclusion, or something like that. So you can use therefore, these 3 little dots. So therefore, the radius is decreasing at a rate of negative 0.03, and the units are going to be the same units in the question. Whoops, except we're talking about radius is centimeters, volume is centimeters cubed. So centimeters per minute. Okay? That is the answer to this question. Okay. So yes, the question is this okay to put decreasing and a negative there? I'm fine with that. I'm not going to ding you for being a double negative there. Do you need the negative? No, not if you write decreasing. That's fine. Decreasing at this rate, totally fine. If you say the rate of change of the radius is negative 0.003 and then don't mention decreasing, you would have to have the negative there. Okay? So either one's fine. Show me your work, let me see the negative there and everything like that, and then it won't be an issue. Okay, so that's your intro to related rates and one example, and we'll do some more examples here coming up. Example 3. Here's the example. A spotlight on the ground shines on a wall that's 10 meters away. Watching carefully. I'm doing this for your good. Thank you. A man, 2 meters tall, walks from the spotlight towards the wall at a speed of 1.2 meters per second. How fast is his shadow on the wall decreasing when he is 3 meters from the wall? Alright, now, if you're just given this question, it's very, very important to draw a diagram. You need to draw a diagram. You need to sketch a diagram. So this is part of the solution. Okay? So I'm just going to go through this as you copy this question and the part of the solution down. Alright? Yes, 2 meters tall. That's what the question says. Okay. Good. Good for you. So, spotlight is on the ground. Man is 2 meters tall and walking towards the wall. Now, do we know exactly where the man is? No. We don't know where he is, but do we know about, the fact that we have 10 meters from here to here? Let me draw that on there. Okay. Because you might wonder where there's x and 10 minus x. So this is 10 meters. The spotlight here is 10 meters away, right? So do you see that we have a triangle? So you should see that we have this triangle. Because we have a wall and it's perpendicular to the ground. Alright? We have a man that's 2 meters tall. Okay? So do you see similar triangles here? Alright, so we've got triangles. There's a 90 degree as well. His height is 2. Now, okay, if we're going to label this wall the height of his shadow, you can label it whatever you want. Okay, x, y, whatever. So in this case, I'm going to label this y. And down here, okay, this section and this section, all right, we're going to want to label these parts. And if the whole section is 10, okay, what you're going to want to do is, remember, you want two variables. Because we're going to differentiate two variables with respect to time. So y is one of them. You got to make x something else. And if you're given that this is 10 meters away, make this section or one of these sections x, and the other one 10 minus x. So it's important to set up your diagram so that you have two variables. And you want to look for ways that they are mathematically related, right? So look for relationships here. So, what do you see? You see the variables, and we're going to see triangles here, right? Okay, so that's one thing that we notice. And they're similar triangles. Okay? So, and they're right triangles too. Right triangles. So how can we express x and y kind of in communication with each other? Well, actually, before we get into the equation, let's just try and connect what we're given in the question with our diagram. Okay? So 2 meters, we see that. He walks from the spotlight towards the wall at a speed of 1.2 meters per second. So what is changing at 1.2 meters per second? Which part? The rate of change of what? No. The man walks toward the wall. X is changing, right? So x prime is 1.2. You see that? The rate of change of x. His distance from the wall is increasing at a rate of change of 1.2 meters per second. So this is a speed, which is a rate. So that's going to be x prime in this case. Okay? Got it? That was good. Got it? So the question says, how fast is the shadow decreasing? Now, if you think about it, this man is this tall as he walks, okay? So this is him, right? He's walking still. And the shadow is going to get smaller as he gets closer. See that? So his height stays the same, but the shadow is going to get, lower and lower on the wall. Does that make sense? Until he's right here and the shadow's the same height as him. So what's decreasing? The rate of change of y. Okay? So y prime is what we're looking for. So how fast is the shadow on the wall decreasing when he is, 3 meters from the wall? Right? So 3 meters from the wall. So how can we represent that, 3 meters from the wall? Well, this distance has to be 3. So if this is 10 minus x, 10 minus x must be 3. So what's x? So when x equals 7. So I usually put the at sign here, at x equals 7. So when it says when, this information, okay? So again, the tricky part is diagram, labeling quantities, relationships, equations, okay? That's definitely can get tricky, right? So the more of these questions that you see, the more you understand we're looking for two variables, looking for relationships. Write down what you're given, and write down what you need to find. Then you can kind of look for relationships here. So at this point, we want to try and figure out, and this is, I know everything's really messy here, so I'll get rid of some of this stuff. But at this point, we want to try and figure out how are, x and y related. How can we write x and y as an equation? How can we put them into an equation? What are some ideas that you have here? Well, right triangles, could we use Pythagoras' theorem? If we use Pythagoras' theorem, we'd have to come up with basically other quantities here, right? For like hypotenuse and stuff, and you don't want to do that. You don't want to introduce too many more variables, okay? All right, so let's just clean this up a bit here. Similar triangles. What do we know about similar triangles? Remember way back when similar triangles? 45, okay, well you got 90 here. We've got a small triangle and a large triangle. And because they share the same angle, these are similar. Which means that, I guess, the ratio of corresponding parts are equal. Alright? So that means that if they're similar triangles, that the ratio between this one and this one will be the same as between this one and this one. So if this triangle was twice as big, let's say, then each side would be twice the length of its corresponding side. So you could look at it like that, and that's going to be the easiest way to do this question. Now, in Chapter 7, we're going to look at how we integrate angles and sine and cos and tan and stuff into related rates. So that's why we did Chapter 7 first to give you a little bit more time to kind of differentiate and all this stuff. But we're going to need this related rates piece to finish off Chapter 7. And so we're going to be able to use angles here in our related rates questions. But for now, we're not using angles. So similar triangle, okay? That means that y over 2, because these are corresponding sides, right? This side and this side, is the same as what? 10 over x. Yeah. 10 over x. Okay? So you could kind of go two different ways here. You could, I don't know if I'd suggest this, but you could write this as xy equals 20, right? If you just multiplied like that. You could write this as xy equals 20. Or you could write it as 1/2 y equals 10 times x to the negative 1. Right? It's the same thing. This proportion could be written in a different way. If you take the derivative now, this side you're going to have to use product rule. So, I don't know. Here you just have to use the power rule, really. So, either way, either one I think is going to be okay. But let's say you took this one, okay? Let's say we did that one. So what is the derivative here? In this case, the derivative of this side with respect to time. Okay, of y, sorry, 1/2 y equals 10 times x to the negative 1. Well, what's the derivative of 1/2 y? This is like y to the power of 1, so that's 1/2 y prime, right? 1 times 1/2 times y to the 0 times y prime. So it's just basically 1/2 y prime. Okay, it's a constant in front, so really you can just excuse the constant almost, just leave it there. What's the derivative of y? Y prime. The derivative of this side is very good. Yes, negative 10x to the negative 2. Now, are we done? Got to be careful that we have to remember that x is not our preferred variable, right? So it's times x prime. Okay, so don't forget that. Okay. So we've differentiated here now, and we go back to the question, and we said x prime was 1.2. Okay. So here's x prime, 1.2. I'm just filling everything in here. Okay, what about y prime? Y prime is what we're looking for, right? So we'll leave y prime as y prime. And x, do we have a value for x here? That was 7, wasn't it? So do you see how now I'm able to fill everything in here? And now you can solve for y prime. Okay, so that's going to be negative 10 over 49 times 2.4. Right, which is negative 24 over 49. Or, so the units would be what? Yeah, it's a speed. The distance are given in meters, and also the time reference there is in seconds, right? So meters per second for the speed. Meters, right? Okay, so here we go. Either one is fine. The fraction here or the decimal form, but that is the speed. So if he's moving at 1.2 meters per second, his shadow is moving down quite a bit slower, which makes sense. The shadow would move quite a bit slower as he's moving towards the wall. The shadow would move a little bit slower, but it's also decreasing. Okay, that's that question. Okay, so there's your assignment here for today, and I'll type out some steps for you. Some of you said you want some steps in solving these problems, so they'll be up here in a sec. So the steps that I would suggest for solving these problems would be, first of all, read and understand the problem. So what are you given? What are you asked to find? Write down all your givens. Write down what you're asked to find. Draw a diagram if you're unable to do that, or a diagram will help in all stages of this problem-solving process. So draw a diagram where possible. And number 3, introduce notation. So you have two variables for two quantities usually. And number 4, express the information in terms of derivatives. So remember, we're talking about two rates of change here in these problems. So a rate of change is a derivative, so kind of connect all that. Find an equation or some kind of relationship that relates all the information. So it could be a volume formula, it could be Pythagoras' theorem, it could be just a simple ratio of similar triangles, anything like that, anything that relates the two variables, some equation. Differentiate both sides with respect to time, so that means there's no preferred variable. X, the derivative of x is x prime, not 1. The derivative of y is y prime. The derivative of r is r prime, and all that. Number 7, substitute information into the derivative that you've found. Okay, so your rates of change, your lengths, distances, whatever they are. And note, please don't insert the lengths or given quantities before differentiating. Sometimes students do that. They do that right at the beginning. Oh, I'll just insert my radius here. I'll just throw that in right away, and I'm done. I found v, done. That happens, actually, and you want to make sure that you differentiate first, okay? So there's the steps I would suggest for solving these problems, and yeah, that's that. Good luck.